All right, pretty soon we're going to get to one of the cooler parts of machine learning, but at least I think so, called decision trees. But before we can talk about that, you need to understand the concept of entropy in data science. And it's a pretty simple exercise, very short lecture here, but let's just get that concept under your belt. Let's talk about entropy, another example of a fancy word for a simple concept. But we need to understand this before we talk about decision trees, so let's get this under our belt first. So entropy, just like it is in physics, thermodynamics, it's a measure of a data set's disorder. So how same or different is a data set? So imagine we have a data set of different classifications, for example, animals. Let's say I have a bunch of animals that I've classified by species. Now, if all of the animals in my data set are an iguana, I have very low entropy because they're all the same. But if every animal in my data set is a different animal, I have iguanas and pigs and sloths and who knows what else, then I would have a higher entropy because there's more disorder in my data set. Things are more different than they are the same. Entropy is just a way of quantifying that sameness or that differentness throughout my data. So again, an entropy of 0 implies all the classes in the data are the same, whereas if everything's different, I would have a high entropy, and something in between would be a number in between. So it's just another example of a fancy word for a simple concept. Entropy just describes how same or different the things in a data set are. That's all there is to it. This is a very short lecture because it's a very simple concept. Now mathematically it's a little bit more involved than that. So when I actually compute a number for entropy, it's computed using this expression here. So for every different class that I have in my data, I'm going to have one of these p terms. So p sub 1, p sub 2, and so on and so forth through n for n different classes that I might have. And each term, the p just represents the proportion of the data that is that class. And if you actually plot what this looks like for each term, this negative p sub I times the natural logarithm of p sub I, it'll look a little bit something like this. And you add these up for each individual class. So if you look at it, it kind of makes sense. For example, if the proportion of the data that is a given class is 0, then the contribution to the overall entropy is 0. And if everything is that class, then again, the contribution to the overall entropy is 0. Because in either case, if nothing is this class or everything is this class, that's not really contributing anything to the overall entropy. It's these things in the middle that contribute entropy to the class, where there's some mixture of this classification and other stuff. And when you add all these terms together, you end up with an overall entropy for the entire data set. So mathematically, that's how it works out. But again, the concept is very simple. It's just a measure of how disordered your data set, how same or different the things in your data are. That's all there is to entropy. So with that under our belt, we can move on and talk about decision trees. So that's entropy, just a measure of the disorder of a data set. How same or different is it all? And you just need to understand that as we talk about decision trees up next.